Hello everyone, welcome to the UFS webinar series. This webinar series is hosted by National Weather Service, Office of Science and Technology and Integration. The goal of this webinar is to enhance the communication and share the advancements in all aspects of the UFS in both research and operational settings. My name is Bhavana Rakesh and I work with Yang Yue, who is the program manager at OSTI, to coordinate and deliver this webinar. Feel free to contact us if you have any comments and suggestions. Today's webinar is going to be presented by Dr. Robert Hallberg from GFDL. He will be introduced by Dr. Runjan, who's the lead for Oceans Division. Before we get started, I'd like to quickly show you how the webinar notifications are shared and where you'll find it on the UFS portal. If you go to the UFS portal, which is hosted at ufscommunity.org, we have a box called Upcoming Events where we share the announcements of the upcoming webinar, and there's a link for the abstract and registration, which will take you to the registration page. To look up older archived webinar events on the website, if you scroll down to the Stay Connected section, you can click on the View Webinar on YouTube, and it takes you to the archive page where all the webinars held so far have been listed. And it's over here. You can also subscribe for upcoming announcements by clicking on this Google form with this button. And before we get started, I'd like to go over a couple of housekeeping items. The microphone and webcam have been disabled for all the attendees. Raise your hands if you would like to be unmuted. We plan to have the presentation for about 45 minutes, followed by a Q&A session for 15 minutes. During the course of the webinar, you can feel free to type out your questions in the question box. And Dr. Bob Hallberg will read the questions, or if there are any technical difficulties, I will be reading them out aloud. With that, I hand over the stage to Dr. Runjan to introduce Robert Hallberg.
Good afternoon. It's my pleasure to introduce Dr. Bob Hallberg, today's speaker for the UFS webinar series. Dr. Hallberg is an oceanographer at NOAA's Geophysical Fluid Dynamics Laboratory, Ocean and Cryosphere Division. He is co-leading the development of MOM6 ocean model and the SIS2CS model. He has made significant contribution to the dynamic algorithm of MOM6, as well as the parameterization of a wide variety of oceanic physical phenomena such as boundary layer turbulence, shear mixing overflows, and eddy-driven stratification. Some of his other work has considered the large-scale dynamics of the turbulent Southern Ocean, or sources of systematic biases in the projection of sea level rise. Dr. Hallberg has served on several committees that carried out studies for U.S. national academies, and recently served as one of the lead authors of the Changing Ocean chapter and the summary for policymakers in the 2019 IPCC Special Report on Oceans and Cryosphere in a Changing Climate. So today he will talk about the MOM6 Community Ocean Model and its operational use across NOAA. So please join me to welcome Bob for the webinar.
Great, thank you very much, Rom. So it is my pleasure to be able to address the UFS webinar today. And I think it's interesting to note that although UFS has been going on for a couple of years and has had some really notable successes in developing the next generation of weather forecasting models, this is the first time that we've started to talk about coupled models and the ocean side of things. And this is kind of a very natural outgrowth of the fact that the weather forecasts were the absolute top priority that had to be delivered on time. But now that is working so very well, we're starting to broaden, as a part of UFS, the scope of what's being actively worked on. And so it's my pleasure today to talk about the MOM6 Community Ocean Model and its operational use across NOAA. And as I'm doing this, I'm really going to address kind of three different topics here. The first is, what is it about MOM6 that makes it a good candidate for use for such a wide variety of applications as is necessary for all of the operational uses in NOAA and beyond. Second, I'm going to go through a number of the applications that are either already going on or ongoing that are either operational or kind of quasi-operational. And here I'm going to include, say, coupled climate forecasts in that kind of quasi-operational mode. And then thirdly, I'm going to also talk about how we've managed the testing and the quality control, the integration of the MOM6 community, which I think is something that is working very well and is really kind of a template in some ways that might be useful to think about for some of the other community models, or there are things we can learn from MOM6 for the other community models that constitute the unified forecast system. So the first question is, well, what is the MOM6 ocean model? Short way to describing it is it's a community ocean model with roots in climate modeling. So we emphasize things like very careful conservation of heat and salt, the ability to run in global domains, and the ability to work even in when the conditions are changing. So for instance, as the climate is warming or cooling. It's relatively straightforward. It's a structured sea-grid model with a finite volume core. And in this, it shares an awful lot in common with a number of the other widely used large-scale ocean models, for instance, ROMS or MIT GCM or HICOM. But although it has a focus on global climate modeling, a lot of its applications have also been used to study processes that are relevant to governing the ocean. It's hydrostatic, and as I said, with its emphasis on climate modeling, we've taken a great deal to make sure that it is conservative to round off of everything that matters, including in cases where we have wetting and drying. The emphasis there really being on looking at, say, moving grounding lines under ice shelves and ice sheets. The technique here that makes MOM so flexible is known as the vertical Lagrangian remap method. And the idea here is one that we can illustrate by kind of looking at the primitive equations that it solves. You can write down the momentum equation, the continuity equation, and the tracer equation in a generalized S coordinate, as is done here. If you're familiar with these equations, they'll be old friends. If you're not, don't worry about the details. The main thing, though, is that you can split up these dynamics into two separate pieces that can be solved in separate phases. The first one is a Lagrangian dynamic update, which basically treats these as the shallow water equations with outflow across the surfaces. And so the momentum equation, that's most of the terms here. It's basically F equals ma, but moving with the coordinates in the layer, in the vertical. As you get vertical motions, for instance, as you see here in this picture on the right, you'll see that this is a downward plume with a kind of a nose that's rolling up into a big vortex in this dense overflow. And then the continuity equations in this Lagrangian phase are used to predict the vertical motion of the interfaces. dPds, S is the coordinate, dPds is essentially the thickness of each of these layers. And so in this case, this is being run in a way that we will be remapping it back to a height coordinate, back to perfectly flat surfaces periodically. But we don't have to do that every time step. That remapping is something that occurs as a part of this red remapping step, where you pick a target coordinate and you move it back towards it. And that target coordinate can be, well, it can be anything sensible. And the definition of sensible is you want things to be monotonic in the vertical. It is a vertical coordinate after all. You don't want your layers to get too horribly tangled and so on. But there's a great deal of generality in what you can do. And so you can use this to emulate any of the traditional coordinates that have been used in ocean models, be they height coordinates or a terrain following coordinate, a density coordinate. Now, the tracer equations are interesting because although these tracer equations are also being split up, they're being split up in such a way that you don't actually need to advect tracers in order to get gravity waves. The vertical motion associated with the gravity waves comes from the vertical motion of the layers. And so you don't need necessarily to step the tracers with the same frequency with which you step the rest of the system. And so this allows us to think of there being essentially 4 completely separate time-stepping cycles in MOM6, ranging from a very fast time-stepping cycle associated with the fastest motions in these hydrostatic primitive equations, the external gravity waves. So these are two-dimensional linearized momentum equation, but with a time-integrated continuity equation to allow, for instance, for the wetting and drying and for essentially a perfect reproduction of what the sum of the layers would do. But because they're two-dimensional, they're relatively cheap. We step this with a very short time step that's maybe about a factor of 100 faster than we used for the Lagrangian time step, that blue part, which is essentially the stacked shallow water equations, including the vertical movement of the interfaces and the layers. And then we can integrate the transports over several of these Lagrangian dynamic steps and use those for the tracer equations. And this is where this system becomes particularly effective in Earth system modeling applications where we might have dozens of tracers that we'd like to carry around. Because we don't have to step those dozens of tracers with the short time steps that you need to resolve the internal gravity wave dynamics or the inertial oscillations or other more rapid motions, we can take a longer time step, and therefore they're relatively inexpensive to add these tracer advection equations, additional tracers to be advected around. Now, along with these, we also apply at the same time the thermodynamics, including vertical mixing, essentially what those of you from the atmospheric community might think about as the column physics part of the system. And then finally, we periodically remap towards our target coordinate systems. And this is something that you can think of as essentially a discrete step where you've allowed the motions to carry around the interfaces, excuse me, and then we will periodically remap them back towards whatever our definition of our vertical coordinate is. Okay, so the nice thing about this is that gives us no vertical CFL limit on our time steps. For other types of models, it's often the vertical advection that limits the length of a time step. And it allows, in some cases, for us to reduce the numerically induced diapicnal mixing, especially when we're tracking a density-like coordinate, as is shown up here in this top panel. But it gives us a great deal of efficiencies for biogeochemistry and a variety of passive tracers. Now, MOM6, with many contributions from the communities and extensive collaborations, has become fairly comprehensive in its list of available physical process parameterizations. Essentially, we have everything that would be required for a climate model projections, including parameterizations that are designed to work even when they're outside of the observed range of conditions. In other words, we're very careful to make sure that as we're extrapolating, we have physically based parameterizations. We expect them to work equally well at the last glacial maximum or in a future state where, say, the ocean is significantly warmer than it is now. And increasingly, we're moving towards building a lot of them around kind of an energetics-based formulation. As I mentioned, many of these capabilities have come from external collaborations, and I will speak a lot about this at the end of the talk. We're also doing a lot to embed the cryospheric models, the sea ice and the icebergs into the model, basically reflecting the fact that if I, for instance, take my glass of water here and I put an ice cube in and I slosh it around, the ice is actually a part of the same dynamic system as is the ocean water. And so we're using the dynamics of the ice and the ocean in such a way that it captures this fact that they're tightly tied together. But the bottom line on all of this is done in a community open development framework with thoughtful software design that drew upon lots of experience, some cases mistakes from many predecessor models. And so that you'll see a lot of this in the material I'm presenting today, where I'm only personally responsible for a very small fraction of what I'm showing. Instead, a lot of this is coming from our partners in the MOM6 community of users and developers. So there are many different applications that MOM6 has been applied to. It's been used for everything from say idealized process studies like this 2-layer system where we're looking at the baroclinic dynamics and how to represent eddies, all the way up to something as comprehensive as GFDL's CM4 coupled climate model that you can see here. We've been using it for ice sheet ocean interactions. NCAR has made the corporate decision that MOM6 is going to be the primary ocean model used with its next generation Community Earth System 3 model. There are external, significant external groups, for instance, the Australian COSIMA consortium that are using it. And increasingly, kind of reflecting some of the nice properties when it comes to using MOM6 with lots of tracers, it's being used and configured for regional use for fisheries management question. And I'll say a bit more about that later. In terms of UFS, it is going to be used as the ocean component of the replacement for the CFS V3 coupled seasonal forecast system. And increasingly, we are working with partners closely connected to the Navy under funding from the National ESPC to look at using MOM6 as the successor for HICOM in the high resolution near-term forecasting systems that the Navy and NOAA both use. And this is reflecting the fact that there are many significant similarities between HICOM and MOM6, but there are also some important differences in terms of say, the community testing aspect of it, and also this pedigree of MOM6 coming from the climate community. So today I'm going to be talking briefly about a handful of proto-operational or operational uses of MOM6 in NOAA, just illustrating the broad range of things that MOM6 is being used for. So I'll be talking about the GFDL CM4 and ESM4 global coupled and Earth system models and some of the variants of them. I'll speak briefly about MOM6's use in subseasonal to seasonal forecasting. And this is something happening both at EMC and also at GFDL via the North American Multi-Model Ensemble in GFDL's SPEAR model. And then I'll talk a little bit about some of the things we're doing with these high resolution cross comparisons with HICOM, some of the things we're finding. Hopefully set this up for a follow-on seminar by some of the other folks who are working on this to get more into some of the details, and then talk a little bit about the potential for the use of MOM6 for regional applications, specifically tied to the Climate Fisheries Initiative, and how this might interact with some of the other regional ocean modeling activities in NOAA. So this is the sea surface relative vorticity in the CM4 coupled climate model. And I just love this animation because it shows the rich range of physical phenomena that are taking place within this coupled climate system. You'll see the rich dynamics and the rapid timescales in the tropics, including tropical instability waves. You see the dynamics of the Gulf Stream. But my favorite are the hurricanes that are kind of zipping through here and spinning up the ocean. And you'll see them in the various hemispheres as you get into hurricane season. But in terms of the overall quality of this model, one of the things we're quite proud of is that this has a significant improvement over our predecessor models by many climate metrics. Now, GFDL has traditionally used models that are something like 1 degree for a lot of its climate stuff. And that was driven in large part by what was affordable based on the computer systems. But as we go to higher resolution, you could add complexity in terms of more parameterizations or additional biogeochemical properties that you're trying to forecast. You could add more ensemble members. There are lots of different ways that you could use the expanding computational capability. But one of the things we have chosen to do is push towards higher spatial resolutions, but not terribly high. Only 1/2 degree and 1/4 degree were affordable last time around for use in, for instance, CMIP6. And the question is, well, why just make those incremental steps? So as you go from 1 degree to 1/2 degree, you pick up stronger boundary currents, you are able to better represent the topography. And then as you start to go to higher resolution, you start to be able to permit large eddies in some of the ocean basins. And so we've used this 1/2 degree model, which is significantly cheaper, for our Earth system model, which has a large number of biogeochemical tracers. The finer resolution is the one that we use for our coupled model. Now, within our coupled model, one of the things we're quite proud of is that by using a hybrid vertical coordinate, we're able to greatly reduce the amount of spurious vertical mixing that occurs in the ocean's main thermocline. And this is illustrated here with the 3 models, 2 of which are identical resolution and differing only in their vertical coordinate. The first one is a Z coordinate model, and this exhibits kind of a spontaneous drift due to vertical mixing, a warming of the lower main thermocline. This is the horizontal mean temperature as a function of depth and time in the control run for our climate models. And you can see that the Z coordinate model, our first attempt, showed significant warming, significant drift, a significant broadening of the main thermocline. And this is something that's been noted before as you start to get into eddy permitting regimes. Whereas by using a hybrid vertical coordinate, a pressure-like coordinate near the surface, and then tracking density surfaces in the interior, we're able to greatly reduce this drift from what we had gotten with a traditional Z coordinate model. As we go to, and in this case, we didn't have any parameterizations of mesoscale eddies turned on. We're just letting the model do what it's going to do. As we went to the Earth system model, where we were adding lots of biogeochemical tracers, we reduced the spatial resolution, but added parameterizations along the lines suggested by Gent and McWilliams in order to maintain a minimal drift. Now, within our coupled model, we do have a very simple Earth system model that we use to predict chlorophyll mostly. And it sort of works with only 6 biogeochemical tracers. But in our full Earth system model, we have a rather robust set of 33 different biogeochemical tracers and a full ecosystem, all the way from nutrients all the way up to zooplankton, and are able to use this to address a broader range of questions about how the ocean ecosystems are going to respond to various forcings, to climate change, and so on. But one of the things that we're really proud of is just how much this new generation of coupled model has been able to reduce the systematic biases. So we've seen, for instance, our previous generation of coupled models, each of which had RMS sea surface temperature biases of order about 1¼ degree. Those are down significantly in both of our CMIP6 generation of coupled model and our Earth system model, with the RMS errors here dropping quite significantly. This is something that's reflecting significant improvements both in the atmosphere and in the representation of the ocean, but it means that we're capturing more of the dynamics of the Earth system a bit better, and hopefully this is a more useful tool for projecting how the world will evolve. However, we're also noting that the resolution that we could afford to carry out this large range of simulations is pretty limited in what it can do in terms of its ability to explicitly represent mesoscale eddies. And so following on from this, we at GFDL are working on a hierarchy of higher resolution coupled and ocean-only models And here in the bottom right, you see the surface speed in a 1/8 degree variant of this previous 1/4 degree model, with the kind of the goal being to resolve enough scales to start to admit first baroclinic mode, basically mesoscale eddies, over a larger range of latitudes as we push to higher resolutions, as illustrated here in the bottom left. And as we do so, we found that we're able to obtain very similar climate signals, large-scale climate signals. So some of the big things we've been looking at actually carry over very nicely from one resolution to another. This, for instance, is the 50-year zonal mean change from the late 20th century to the early 21st century, as compared with the observed trend from our new 1/8 of a degree variant and our previous 1/4 degree variant. And these are very similar. So we think that we're building a whole hierarchy which can be kind of mutually supportive instead of detracting from one another. Now, also at GFDL, these same tools, CM4 and ESM4, have been used to build what Tom Delworth's group calls the SPEAR, the System for Prediction and Earth System Research, which is being used for seasonal to decadal forecasting with a full data assimilation ensemble, Kalman filter-based data assimilation system. And then this is being used as one of GFDL's a contribution to the North American multi-model ensemble for seasonal prediction from GFDL. And this same model is being used by people in Tom's group, for instance, to try to separate out the climate signals from noise. In this case, looking at the strength of AMOC in this model, with initialized from observations with data assimilation, but an ensemble of different models to help separate the signal to noise of a potentially important climate signal, and help identify when we might be able to actually observe significant climate changes. Now, that's at GFDL. At the same time, this exact same OM4 1/4 degree model is something that we've handed off to EMC, and hopefully Yan will be happy that I'm still using this animation that she gave me a couple of years ago, illustrating the difference in the sea surface temperature between the previous 1 degree MOM3 with global data assimilation used for seasonal coupled forecasting in CFS v3, with a new replacement where this is using the exact same configuration as GFDL's OM4 at a 1/4 degree resolution and a new higher hybrid data assimilation system. And you can see that there are going to be some significant improvements, even just in the mean structure of things like the front associated with the Gulf Stream, that should help with weather forecasts, as well as the ability to forecast signals in the ocean. And at the same time, we're also looking to develop a replacement for the 1/12 of a degree model that is currently being used at EMC with one that's closely tied to the same 1/4 degree. And this is in close alignment with this strategic vision driving the unified forecast system of simplifying the operational modeling suite. And this is a picture that various people have been using for a few years now to illustrate just how complicated the prediction suite is or was, and all of the different interacting pieces. The idea here is that instead of having lots of different models for different pieces, you would instead build a streamlined system where you can turn on or off different pieces, still at different resolutions, but to address issues related to specific forecasting needs. And as a part of this, the UFS also adopted a very outward-looking community-based approach for how these components were going to be developed. And MOM6 is one of these community components that is contributing to the new unified forecast system, each one of which has its own authoritative repository, its own testing regimes, its own basically way of trying to keep as many people engaged in as useful a way as is possible. This is all about opening up and allowing the forecasting capabilities to benefit from the tremendous capabilities within the oceanographic and atmospheric communities in the US. And the fact that MOM6 is very much an open development, open model, I think goes a long way towards helping to achieve those goals. So there is a new UFS S2S model that is being run and tested out, and Jiande Wang was kind enough to share a few slides kind of describing it. Again, this is the ocean component here is based on MOM6. The sea ice component works on the same grid, but in this case is the CICE version 6 sea ice model. And these two have been successfully used together. And then in runs evaluating how this works in comparison with observations, the results are pretty favorable. So this is a comparison of the January and April mixed layer depths in 30 days runs, initialized from observations. You let the model go, look at it at the end of the month in comparison, for instance, with Argo, and shows a seasonal cycle that is doing pretty well. Similarly, you can look at things like the speed associated with the loop current or the Gulf Stream or the Kuroshio. And so this is one that's tracking reasonably well with observations. Now, the fact that we've only run it that Jiande has only run this for 30 days hasn't really given the model time to really mess up, but it is still quite gratifying that it is reproducing the state of the ocean and holding that for the desired timescale of these forecasts very nicely, and is able to reproduce things like the equatorial undercurrent speed these are again in 30-day runs starting from the beginning of each month, and is doing quite a nice job of reproducing the seasonality with this new prototype for use in the UFS. At the same time, we are also collaborating with Ellen Wallcraft and Eric Chassigny and others on trying to evaluate whether we can unify the Navy and NOAA global ocean modeling capabilities by doing close comparisons between results from HICOM configurations that have proven themselves and been used for several years with MOM6 configurations. And this is a very deliberate activity funded by the National Earth System Prediction Capability. And it really is recognizing that there are overall some very nice complementary designs and strengths of these two models. Specifically, MOM6 has a lot of capabilities that are directly tied to its legacy coming from being a climate model. So very strict adherence to conservation of properties, its ability to use a full nonlinear equation of state, including issues related to pressure gradients, its ability to have sea level evolve over time, and so on. While at the same time, the Navy has really made some tremendous investments and developed a great deal of expertise in things related, for instance, to real-time data in ingest and feeding it into the data assimilation system, getting systems that just work robustly every time, all the time, and are able to deliver on the mission goals. And so these are very much complementary, and we're learning a lot from each other. Now, overall, they're very similar, but there are a number of different areas where there are some significant differences that we think can be attributed to differences in the numerics. So, for instance, this is the Gulf Stream, 3-year mean Gulf Stream from the two different simulations, and the sea surface height variance. And even though they have the same forcing, the same topography, we're still seeing some interesting differences, for instance, in the magnitude and extent of the eddy field. And by cross comparison, mixing and matching different parameterizations, we hope to be able to capture, for instance, this nice extension of the Gulf Stream eddy field in MOM6, while also trying to figure out what is it about the difference between HICOM and MOM6 that's leading to a difference in the separation point near Cape Hatteras here, which is something that is of significant importance for actual operational forecasts. And these are things that we're increasingly able to attribute to specific aspects of the numerics of the different models, and then by mixing and matching, we can probably come up with, we expect to be able to come up with something that is coming up with the best of both of them. Here's another example where in these 41 layer simulations, this is quite a bit lower vertical resolution than we had been using in our climate models, but the overturning circulation in the 41 layer HICOM is doing reasonably well with a very nice deep North Atlantic outflow, much deeper than we were getting in the 41 layer global MOM6. And by going back and looking in diagnostic balances to try to figure out how they're differing, one of the things we found here was that we were perhaps remapping to density surfaces too aggressively in this high resolution eddying model. And so by slowing it down, by not forcing the coordinate surfaces to get back to the target positions abruptly, but slowing them down, we were able to reduce some of the mixing that we think is contributing to these differences in the overflows. And there are other algorithmic changes that we think are suggested based on these comparisons, thinking, okay, instead of just kind of using these simple methods, are there better ways that we can reformulate the system so that it works more adaptively, more automatically in a wider variety of different parts of parameter space? And I think this is really kind of a nice illustration of the way that having different groups with different applications of the models, but using common tools, allows us to learn from each other, allows us all to make each other better going forward. And here's another example. In this case, this is the third area where HICOM was exhibiting some significant, was significantly better than the MOM6 12th of degree simulation, is in the loop current shedding. HICOM was shedding loop currents regularly. MOM6 by comparison was shedding them much less frequently than in fact is observed. And this is something where by close comparison and then starting to swap some things in and out, we think this is something that's related to the details of how the bottom drag and the lateral side drag parameterizations are implemented in these two models that's contributing to this destabilization or not of this loop current eddy. And so we think that we're going to be able to learn from this and improve MOM6 pulling in capabilities of HICOM and really paving the way for this same modeling system to be used by the Navy and NOAA across a wide range of different scales. And then the other emerging area is the use of MOM6 for regional modeling. And now, of course, regional modeling is something that's been done for a long time, and it essentially permits you to put in much finer scales and resolve smaller features than you could if you're modeling the whole world. But the MOM6 algorithms are particularly attractive for applications that use lots of biogeochemical fields, such as regional ecosystem modeling or fisheries. Again, because you don't have to use the short time step dictated by the dynamics for all of the tracers, and the number of tracer fields in a comprehensive ecosystem model gets to be quite large, to the point where if you don't have this difference in the time steps, the ecosystems vastly dominate the costs of your calculations. And this is one example of this fairly high resolution regional application of MOM6. This is work that was done in collaboration with Enrique Kirchitzer, Ralph Dusen, and a whole group of really talented people in a configuration that's been used with ROMs for quite some time. This is the surface vorticity with open boundary conditions, and one of the things that I think this illustrates is that the open boundary conditions are working quite well. You're really not seeing too many boundary artifacts coming in to this simulation, quite apart from being quite an attractive animation. There are some that are there, but they're subtle, and we're working on even improving those, but we're quite pleased with how this is working in a regional configuration. But this adds kind of an added complexity when we think about how this fits with things that are already going on. Now, this is a diagram, much like various ones that people have done for various things, looking at the spatial scales and the temporal scales associated with different physical phenomenon or with different decision points. And when we're thinking about fisheries specifically, there are a very broad range of spatial scales and temporal scales or time horizons of action that have to be brought into account. And so this is maybe giving us a way to kind of think about how to develop new capabilities drawing from the community without stepping on the toes of people who are doing this every day, and build up kind of a collaborative partnership slowly over time instead of abruptly, and letting it basically evolve naturally. And here I would note that the National Ocean Service has a very extensive coastal ocean modeling program, which does routine forecasts of the flows, the water properties, the conditions in all of the major ports around on the ocean side of the continental US and around US territories, and is really working to deliver near-term forecasts, something of order a week sort of timescales, that answer a lot of questions of real value and importance to people, and we wouldn't want to do anything to disrupt that. But these are, in many cases, now they use either the ROMS Ocean Model or FVCOM, and the idea here is that there are a lot of similarities, structural similarities between ROMS and these, what we can do with a MOM6 with a hybrid coordinate. But MOM6, because of the way that we can take long steps with tracers, makes it a really good candidate for answering a lot of questions that are needed on the fisheries side. So our emphasis here, and this is something that is being funded now with the Climate Fisheries Initiative, is to develop a series of regional basin scale configurations of MOM6. They'd be forced at the boundaries from the global configurations, but really with a focus on spanning the areas around the US with a platform that is useful for studying ocean ecosystems and questions specifically related to fisheries. And so over time, what we're envisioning is that these larger scale questions related to fisheries specifically and Earth system modeling would be coming from this MOM6 capability, whereas the existing National Ocean Services work on regional predictions are coming up from the smaller scales, more locally targeted, with the idea that we can kind of meet in the middle and over time exchange capabilities, become comfortable with one another, maybe even look at importing some of the capabilities from ROMS, working in collaboration with those capabilities in a way that allows a lot of NOAA's needs to be met, but with really careful attention not to step on the toes of anybody who's already working in this area. So I'd like to take just the last couple of minutes to say a few words about how we're doing the open development, working as a collaborative community via GitHub. We're doing something that it's basically open development. Whatever new thing we're doing is immediately visible from the time we do this. And we're working on this with a kind of a framework where there are, say, 6 different major branches, each of which has a slightly different focus, but is a point of contact for multiple users. But each one of these major forks, major hubs, is responsible for doing all of the routine testing, regular testing, to make sure that any of the configurations that hub cares about, be it EMC or be it GFDL, isn't affected by changes to the model. So as, say, some new capability is contributed by a user, that would first pass through the GFDL hub, which would evaluate things, carry about regression tests. But then once they're passing those regression tests, that's something that we offer up to the rest of the community. But all of the synchronization here is always done by consensus and under the principle that we will try to accept things as long as you're not breaking things for somebody else. And so we have objective ways of evaluating that. First one is with extensive testing, extensive regression testing of anything that works. These are short versions of large-scale models, full models. But also there's an extensive set of self-consistency testing that we do with MOM6. And this self-consistency testing is something that any user can do anywhere. They get immediate feedback. Did it break? Did it not? Is it identical? Is it not? And so they can fix it before they even offer it up to this larger group. And so far, we've been doing this for about 4 years now. We have been able to keep all of these different major activities working together, working by consensus, and manage to keep all of the different efforts using MOM6 tightly integrated to avoid any kind of long-term splitting up into separate efforts. So with the regression tests, each of the major centers will carry out what they define as their own set of specific tests. They are particular to their computer, and they make sure that they get exactly the same answers unless they expected and wanted the solutions to change. And the objective here is once you have a solution that you think is right, the regression tests make sure that you never lose it, that it never breaks. At the same time, MOM6 has a whole set of self-consistency tests. And for each one of these, you have to get bitwise identical answers. In other words, they are either right or they are wrong. There's no maybe about it. And some of these are common to many other models. For instance, all of GFDL's models for years now have made sure that they reproduce across processor count and layout, that they reproduce across restarts. But we also have tests of rotational symmetry, exploiting the fact that that MOM6 uses a structured grid. We have tests related to what kind of memory you're using. We have tests that look at whether the parameters that you put in are actually the parameters that you actually used. And then finally, this is one that I think is quite unique to MOM6. We have a way of testing for dimensional consistency by rescaling different units by integer powers of 2. And so we're able to use this to test for dimensional consistency of every expression in terms of their units of length, time, density, thickness, heat content, and so on. We have 6 different units, and eventually it could become many more, especially with Earth system models. And the beautiful thing about this, when you've run this test, you have proven that your model is dimensionally consistent. Using this, we've been able to identify and track down dozens of very subtle bugs that we had no other way of getting that. But the nice thing about this is any user can run these self-consistency tests. If they fail, they unambiguously demonstrate that the system is wrong. They don't require access to any particular computer. And we found that they provide really useful feedback to improve the quality of things before they're even candidates for contribution. Given the time, I'm going to skip over this, but I would just like to note that all of this extensive testing is really going to help us out when it comes to thinking about porting MOM to different computer architectures. The robust testing will help with the debugging going forward. So the take-home messages here that I'd like to leave you with, first is that MOM6 is built on a diverse, growing, and open community. And it's building on the existing strengths of a number of different groups, some working on operational side, some of them on research side, some in academia, some in government. But we think that this is a nice avenue for developing a structured ocean modeling capability that respects the dynamics of the marine system across a very wide range of spatial and regional scales. It's already demonstrating its value at both global and now at regional scales, large-ish basin scales, for operational forecasts at things from weather to climate timescales, and it will be one of the major components. We're happy that it's one of the major components of the growing and emerging unified forecast system. We're using it in regional Earth system models in collaboration with NOAA fisheries, to looking at things like the CM4 or ESM4 coupled climate systems. the open development here is absolutely, I think, critical. It gives all of the users agency to control what they're doing with the applications they care about, but also it provides a framework in which people can make contributions without having to worry about making mistakes. We're pretty good, I think, at catching mistakes. And so if you're not afraid of making mistakes, you can contribute, which gives you a way to allow new users, new students, a broader range of people to try contributing, and then giving them the feedback that help them to be able to contribute things that are going to be up to the quality that we all expect them to be. And it's that robust testing and quality control that's absolutely essential for making this open development work and work well. And finally, one of the big drivers here, and I think this is, I've said it many times already, that's worth pointing out, is this is particularly well suited for incorporating very comprehensive marine ecosystem models into our ocean models, because of the separation between the physical timescales and the natural timescales of the Earth system models. We think this is actually a very good candidate for getting us around the problem that we've been facing for a few years, as the desire for much more elaborate, much more comprehensive Earth system models has kind of knocked heads with the constraints of the available computational resources. And so we see in MOM6 and this growing consortium a tool and a paradigm that can be used to address a very wide range of ocean modeling needs to address NOAA's mission. Thank you very much.
Thank you, Robert. There are a few questions. If you can't see them, I can read them out to you.
Let me see if I can open up the window here. Maybe you could read them out for me. I'm juggling tiny windows.
Okay. No worries. The first one is by Joshua Fu. He asks, is there stability issue if the top level of MOM6 is set as thin as 5 centimeters? Now the top layer is 2 meters.
Okay, so in general, no. We routinely run MOM6 where the top level can be an angstrom. There can be some coupling issues. So depending on how you've written your coupler, there are a number of coupled feedbacks that can come into play. Specifically, if you have an explicit formulation of, say, the wind stresses as a function of the ocean velocity, if your effective vertical resolution, this is the vertical resolution after you've taken into account tight implicit coupling by thin layers in the surface, gets to be small enough that essentially a piston velocity times a time step is less than that boundary layer thickness. There are issues related to the coupling. These arise most prominently when we're looking at coupling between the ocean and the sea ice, where if you have significant melting, that can give you a very shallow boundary layer. And one of the ways that we're dealing with these is to embed the ice dynamics and the ocean dynamics together as an option. This is using SIS2, not CICE. Although if it works as well as we expect, then that's something that can be expanded. And similarly for both the thermodynamics and the dynamics. But in general, we are able to run MOM6 with very, very thin layers. And it's mostly that all of our vertical processes are done implicitly, and then the vertical remapping as the way of doing the vertical advection. We're remapping throughout the entire water column. There is no vertical CFL limit that we have to worry about.
Okay. The next question is by Hernan Arango. He asks, do you introduce shocks the system during the remapping, say vertical velocity?
Not that we've ever found.
Okay.
So for the vertical remapping, we're using there's a whole whole system here that Alistair Adcroft and Laurent White worked out. We're mostly using piecewise parabolic methods, but we're also careful in how we do both the edge value, the location identification, and then the vertical remapping. So we tended to use piecewise parabolic or piecewise quartic methods in the vertical. I don't think that I can think of any instances where we've seen significant shocks in the vertical that become overly problematic. But that's a very good question.
The next one is also by Hernan. In the hybrid system, how do you discretize the bathymetry?
It's a continuously basically you represent as the depth at tracer fields. There are no limitations on the variations from cell to cell. We've never found we had to do any kind of smoothing, but you mostly represent it as kind of the cell average depth on the tracer points. Although one of the things that we're doing in MOM6, and I think we're not unique in this, I think NEMO does this as well. In the horizontal, we can represent the width of open channels as something significantly less than the grid spacing. So for instance, even in a 1 degree model, we can put in the information that Gibraltar is about 12 kilometers wide and that the Bosporus is 1 kilometer wide as kind of a partially open a face that restricts the exchange of waters between marginal seas. And that's something we found is actually really important, especially at lower resolutions, at putting together credible climate simulations representing the exchanges between basins or marginal seas in the open basin.
Okay. The next question is by Henry Zhuang. He asked, do you consider tides from sun and moon in MOM6? I may miss it.
Yes, we can. We have done simulations, both regional simulations with the tides and global simulations with the tides. This is actually one of the significant activities that we're working on as a part of this ESPC activity merging HICOM and MOM6. So you can turn on the astronomical forcing. We have, or you can apply them as in regional domains as open boundary conditions. We have some abilities to deal with the self-attraction and loading terms. The biggest problem, and the reason why we don't tend to put tides into our global models, our climate models, is you need a pretty high resolution to explicitly represent the internal tides, and those are significant. But also, when you've put the tides in, you have to detide all of your diagnostics and your output. And that's something that can be inconvenient. So in a lot of cases, we explicitly put in parameterizations of the effects of the tides rather than explicitly resolving the tides themselves. But we do have simulations that are run with either global or regional tides.
The next one is more of a comment by Arun Chawla. He says the UFS weather model now builds a standalone atmosphere-only mode, a fully coupled mode, atmosphere, wave, ocean, ice, and a marine mode, data, atmosphere, ocean, ice.
Okay, thanks, Arun.
Okay.
And there's a wave model in there too. And actually, that's one of the things, you know, as kind of part of this whole burgeoning collaborations between labs. We've actually had some really nice improvements in the wave model. So the WaveWatch 3, there's some really nice work going on to rewrite it to work with a tripolar grid in the Arctic, which will pave the way for our being able to use the same wave model that's being used for operations for climate projections into, say, a future regime with an ice-free Arctic, where you would like to be able to model how waves are working in this very different Arctic Ocean. So great point about the flexibility of the system, though.
Next one is by Alexander Kurapov. He says, great talk, thank you. How does the S2S model forecast predict anomalies from the annual cycle? Example at the 6 MO horizon.
So that's a subtle question. I'm not sure. I mean, we basically, you run a forecast and then you compare the forecast with a climatology. So you're always, and this is true with any kind of weather model, any kind of climate model, you're always looking at anomalies relative to the climatology of that same model. And that's a way to deal with linear drifts, which might have been the question you're asking, or is a separate question. How does it do it? Well, you assimilate the initial conditions in the atmosphere and the ocean, and you're relying on the predictability of it comes from the ocean. I'm not sure how far we've gotten with the land, but certainly in the sea ice, there's a lot of predictability on this many-month timescale of the sea ice distribution. If you know the sea ice at the beginning of the summer season, it gives you a lot of predictability for what the sea ice will look at the end of the summer season. And then phenomena like the Madden-Julian oscillation has a lot of predictability in the atmosphere. And so it's, if your question is, how is it that you're able to achieve predictability at 6-month timescales? Well, it's drawing upon that inherent predictability in the coupled system. And there's a lot of work going on to try to identify the sources of predictability. I could think of a couple of other ways to interpret the question, but hopefully one of the first two addressed the specific interpretation of the question that you were asking.
Yeah, Bob, we have a lot of questions. If we probably need to answer them quickly, if you can.
Okay.
Okay. So the next one, I'll try to go through them quickly. The next one is from Jiazhu Zhang. He says, for the OM4 1/8 and 1/4 simulations with the JRA 55 forcing, is the data available anywhere for the community to download and analyze?
The OM4, I believe, the 1/4 degree is, the 1/8 of a degree is something that we're still developing, and so we're kind of going through quality control on our own before making that available. But that's a yes. The OM4 has the JRA forcing is at a 1/4 degree resolution based on OM4. Is something that's publicly available, and a number of papers have been written about it. I don't know offhand the location for it, but if you search for it, you should find it. If you can't find it, you can email me and I'll ask around about the exact location where that is. But GFDL serves up the data from the 1/4 degree. The 1/8 of a degree, not yet.
Next one is by Hernan Arango again. He asks, he says, having global and regional connected applications is excellent. I was wondering what can be done to get the lateral boundary conditions to regional ecosystem models.
Yeah, so there are large data volumes. If you're running them in the same place, that's easy. If you're not, that's more of a challenge.
Next
again,
one is,
yep.
Oh, sorry, go ahead.
Yeah.
Next one is by Henry Zhuang. Says for high resolution, land sea mask may change during tidal effect, right? Does MOM6 handle this?
MOM6 does, but our coupler doesn't yet.
Okay.
So MOM6 can wet and dry. There's no problem there. The problem is that if the way we do it at GFDL is we have a land model, and the land model would be what would be responsible for the area that's exposed. And we've talked about this, but haven't implemented it. But having a kind of a mud layer under the ocean would be one way to deal with it, so that the ocean would become responsible for everything that's ever wet. The coupler doesn't need to know whether it's wet or not, although you pass it the information to calculate the fluxes and do it that way. I don't think it presents any particular large intellectual challenges, but it would have to be done carefully and thoughtfully. We have not yet done that specific part.
Next questions by Julie. The vertical resolution of MOM6 can be increased to how high without concern of instability, like 0.1 meter or even higher? And what about the cost to do it if we can?
Okay, so there are two parts of that. There is no limit on the vertical resolution. We routinely run with massless layers, either at the top or the bottom. They can be an angstrom, they can be 0 thickness, they can be as fine as you want. There is no limit for the stability. The cost, everything is done implicitly in the vertical, but it's all done with tridiagonal solvers. So the cost just scales with the number of layers. And when you add the layers, you're marching all the layers forward everywhere. The total cost is of course broken up between the barotropic solver, which is 2D regardless of how many layers you have, and then the 3D solvers in the interior. So it scales linearly with the number of layers.
Next one is from Jabo Zhu. You mentioned remapping frequency. Is there a clear criterion to determine what frequency one should use?
I think that's one where it's more of an art form than anything else. You want to remap back often enough that you're sort of sticking close to the coordinates that you've chosen for some reason. You also don't want your coordinate systems to get too tangled, if you will. But the short answer is we think probably it's something where you want to remap it back with something that respects the dynamics of, say, the biology or the coupling. So of order a couple of hours is enough to resolve the diurnal cycle. But a lot of good research can be done into that question.
Okay, the next one is from June Wang. Can MOM6 run with 32-bit Rel 4? What physics schemes may need updates in order to run the model with Rel 4?
So the problem with Real Star 4 and a model like MOM is that we have equations for the thickness. The free surface height is determined by the sum of the layers in the vertical. If you represent the depth of the ocean in 32-bit resolution, you wind up with a sea surface height anomaly. Basically, the last decimal plate is something like a millimeter. And that's just 7 decimal places compared to the depth of the ocean. And so for the thickness equations and the free surface height equations, you probably need 64-bit precision. For the momentum equations, it's not so obvious, but a lot of the terms are mixed. You're looking at tracer at thickness transports that need to be 64-bit precision. And so it's not obvious how much you would save by going to 32-bit precision. Although obviously this is something we've talked about for parts of the model. It's just not going to work for the continuity equation and the free surface height.
Next question is by Derek Snowden. He asks, are the ecosystem models you're working with community models that communicate with the ocean physics through more standard interface, or are they embedded within the MOM6 code?
There are community models that use the MOM6 code, and the ones that are used at GFDL are heading that way. The ones that are used at NCAR are obviously community code. We have pretty standard interfaces so that when you have an Earth system model, if you have a tracer that you want the ocean model to advect around, you register it, and then going the other way, the way that MOM6 is set up, you the biogeochemical model is responsible for the vertical stuff, so that if you have stuff that's rising or sinking, that's taken care of on that side. But we provide a pretty straightforward interface to do the tridiagonal solver associated with the vertical fluxes and the vertical mixing. But if you go to the NCAR CESM website, there was some discussion about the use of Earth system models in a webinar earlier this year that might be useful to look at. And it is very much intended to be a platform for use with community biogeochemical models.
The last question is by Julia Levin. She asks, can you do coastal applications? Do you have different water types to work in murky waters?
We don't have a sediment transport module yet, although I can't imagine why we wouldn't, but we don't have turbidity contributing to the density as yet. That would be an interesting thing to take on. I don't see anything that would be particularly impossible about that, but we haven't been working on problems for which that was needed as yet. But it's an open development model. If somebody is interested in contributing it, that would be really appreciated.
So that concludes all our questions. Jan, do you have any closing statements to make?
Yes. Hi, everybody. Thank you so much. I cannot believe this. We still have more than 60 people staying on the line, even though we are 10 minutes over. This is the first ocean webinar on the ocean side. We will try to schedule more. If you are interested in giving a webinar, you can fill in the speaker information form on the web page. Like Bob mentioned, we are building the high resolution version of the model and also regional applications. We surely is going to, once they have a good progress, we will try to schedule those progress talk. Thank you everybody. Yeah, feel free to send a question to Bob. Bob, you have a lot of questions already. I'm sure folks have more to send to you through emails. Thank you, Bob. Wonderful seminars.
Yeah. Thank you, everyone. A recording of this webinar will be made available on the UFS portal as well.
Yeah, also the slides are available at the portals. Thank you.